Right, next topic is the PI, which, pH, pKa has something to do with that kind of stuff. This is what's known as the isoelectric point. And the isoelectric point is the pH at which the concentration, remember from Gen Chem, these brackets mean concentration, of Zwitter ion, so has ions but net neutral, form is the highest. Right, so at what pH do you have the highest concentration of the Zwitter ion? To calculate the PI of an amino acid, it's pretty simple. It's just the average of the two closest pKa's. So let's take a look at what that means. So here's just this table, right? Same information that pretty much last table had. Amino acid abbreviation gives you a picture of the structure, molecular weight, pKa, and then of course the PI. So you can see, you can look up the PIs of compounds, right? So in this case, for alanine and most amino acids only have two acidic protons, right? One from the protonated amine, not just the regular amine, the protonated amine, and one from the carboxylic acid. So to find the PI there, you just take the average of those two values. In this case, 2.35 plus 9.87. There's two values there. Divide by 2, you get 6.11. However, some amino acids have more than two acidic protons. So for example, right here, glutamic acid actually has 3 potential acidic protons. That's because it has a carboxylic acid over there, it has that amine, and then it's got another carboxylic acid, right? And you can see some other compounds, right, have the other pKa's and acidic protons as well. And so here's the pKa values, right? You have the one from the first row, it's from the carboxylic acid directly attached for alpha to that amine, then the protonated amine, and then the side chain if there is one. So the PI is the average of the two closest pKa's. So for this compound, we have pKa as 2.10, 9.47, and then 4.0. 4.06, right? My bad. Sorry, I had a little bit of a brain fart. The two closest numbers there are 2.10 and 4.07. Take those, divide them by 2. I actually did an example with a different one in my notes. That's why I'm kind of like all over the place. Let's just do it real quick though. I get 3.085, which actually would round up to 3.09, but close enough, right? You can see how the PI is gotten, right? Just the average of the two closest pKa's. And then the other thing that we want to be able to do is to draw the Zwitter ion. So when we just have two acidic protons, drawing the Zwitter ion is pretty simple. The carboxylic acid is going to be deprotonated, and the amine is going to be protonated, and boom, you got your Zwitter ion. When we have more than two acidic protons, it gets a little bit more complex. So remember that Zwitter ions, in the case of our amino acids, are going to have 2 charges. And so here's how I would do these types of problems. So here's glutamic acid. Right, step 1, I would draw it in its fully protonated form. So all the acidic / basic compounds are protonated. And then in the second step, remove H pluses until we have a net 0 charge. So I'm going to draw this compound, redraw it as protonated, right? So I'm going to take that carboxylic acid, protonate it. Take that carboxylic acid, protonated, and then the NH, the nitrogen will be protonated, so it'll be NH3 with a positive charge. Remember that the smaller the pKa value, the more acidic it is. So we have the side chain pKa value of 4.07. So this one is 4.07. That's the pKa value. We have the amine, its protonated version, has a pKa of 9.47. And then finally, let's see, what color did I pick? This big blue. This carboxylic acid has a pKa of 2.10. And so we're going to start removing protons until we're net neutral, right? We're not net neutral yet because we have a positive charge on the amine and no other charge to balance it out. So what we're going to do is remove the most acidic proton, which is going to correspond to the smallest number, right? So the smallest number is this 2.10. So we're going to get rid of this proton. And we're going to deprotonate it, so we're going to leave behind a negative charge. And now we're going to take a look at our compound, and now we do have a Zwitter ion, right? We have a net neutral charge because we've got a negative here and then a positive here, and then we simply just redraw that. So in this case, the problem is relatively simple, and it looks just like our other Zwitter ions where the carboxylic acid is deprotonated and the amine is protonated, but that won't always be true. Sometimes you'll have to mess with the protons on your side chain. Of course, check out the work along to see how it's done.